Okay, in this video, we're going to be looking at the various properties of atoms now that we've thought about their electron shells and what makes them up. So, what are those properties, and how do those properties change across the periodic table? The first property, and probably the most difficult to understand, but is kind of central to understanding everything else, is this idea of electronegativity. So, electronegativity is quite simply an an element's propensity or ability to attract electrons, right? So you would imagine some some atoms attract electrons more strongly than other atoms. This is determined by what's considered to be the electronegativity, right? Increasing electronegativity essentially means I want to accept electrons, not give them away, right? So if you have a higher electronegativity, it's going to take electrons, and if you have a lower electronegativity, it's going to give electrons. So if you imagine we have two people who are equally strong, you might say that the electronegativity difference is not very much, right? However, if you have a more electronegative element, there's going to be more pull on this side, and then the weaker player or the less electronegative element is going to have less. So if you imagine, if you would like to measure these bits of rope, imagine that this guy would have more rope and this guy would have less rope, whereas this guy has the same amount of rope as that one. So what does the rope mean in this case? Rope means uh, can actually mean size and number of electrons. But let's have a look, before we go on to that, let's have a look at electronegativity trend across the periodic table. Fluorine is the most electronegative, which means that it attracts electrons the strongest. Francium is the least electronegative, so therefore it doesn't attract electrons very strongly. In fact, francium gives away its electron as quickly as possible. And you'll notice that all of these group 1 metals do that as well. So you can probably pick the trend that increasing electronegativity across this way and decreasing electronegativity across this way. Yeah. So you might kind of talk about a general trend from diagonal, kind of low electronegativity down here to high electronegativity up there. So what does this mean when you combine two a number of atoms to make an electron, an actual molecule, right? Well, oxygen has a high electronegativity. Hydrogen has a low electronegativity, so it's going to have more rope, right? It's going to be stronger. It's going to pull those electrons into it. It's going to have more electrons. So therefore, it's going to be bigger in size, and this is going to be smaller in size. That's going to affect obviously the shape of it. You can see it's got a big cloud around the oxygen, small clouds around the hydrogen. It's also going to give it this partial negative charge up here and a partial positive charge around here because there's more electrons. Electrons are negative, remember? So more electrons up here and more positive around here. And this relates to what's called polarity, right? It's polar. It has a negative end and a positive end, or two positive ends, which we might talk about later if we have time. Okay, so here's the trend. Electronegativity um, is directly related to ionization energy. Ionization means becoming an ion, right? Um, uh, so um, increasing ionization energy means that um, it requires more energy to turn it into an ion over here than it does over here. So to turn a hydrogen, a lithium, a sodium into an ion is really easy. You throw it in some water and it'll blow up, right? It's that reactive. It really wants to turn into an ion, really strongly. Turning argon into an ion is very difficult. It's a noble gas, and it won't take on or give any electrons. Chlorine, on the other hand, it's kind of over this way. It will more likely accept an electron than it will be to donate it. Right. So ionization energy is directly related to its ability to take on those electrons. Yeah. You can imagine these would turn into negatives and these would turn into positives, because these are more likely to take on electrons than those are, because they have a higher electronegativity. And that obviously relates to radius, right? If it's more likely to attract these electrons, it's going to be smaller, right? It's going to pull those electrons in, right, and have a smaller size. This is also related to something called core charge. It means that the number of protons in the nucleus are more as you move across the period, right? That's 1 proton, 2 protons, 3, 4, 5, 6, 7, 8, right? So these, the fact that it has 7 protons in here is going to pull those electrons in more. Right? You'll also notice that the size increases as you go down the periods, and this is because the periods represent another shell, right? As you get another shell, you would imagine, thinking about the Bohr model, if you can imagine it in your head, each shell is going to increase the size of these elements. So atomic radii, as we we're kind of saying, increases in size as you increase the shell, and it increases in size as you decrease the electronegativity, right? If it's not attracting the electrons very much, they have more room to spread out. Reactivity is related to the same thing, right? Metal reactivity increases as the metal is more likely to give away its electron. If it has a very low electronegativity, if it's not going to attract that electron, right, then it's more likely to give it away. If you don't hold on to your electron very strongly, you're more likely for someone to take it out of your hands, right? On the other hand, non-metal reactivity increases as you go this way. So for these ones, because they're more likely to take on an electron, non-metals become negative ions, so they're more likely to become a negative ion as the electronegativity increases. So for reactivity, just the metals increases this way, just the non-metals increases that way. Increasing metallic character. If we think about metallic character being the properties of metals, they're shiny, they conduct electricity, they're, whatever else you want to think about, malleability, you can bend them and you can pull them into wires. More likely to be metallic character over here, calcium, zinc, chromium, barium. These are more have more of these metallic properties than what's over here. And we're going to. This is a bit of a tricky one, but again, it's related to metallic to electronegativity. Very quickly, if it holds on to those electrons very weakly, they're more likely to be passed between different nuclei within a metal, right? And as they get passed more and more often and readily, it eventually becomes more like a shared electron that floats between all those nuclei. But we'll worry more about exactly how this cloud of electron occurs and how that relates to electronegativity as we go on. So what have we learned? Electron affinity or electronegativity increases as we move this way. Ionization energy increases as you move this way. Atomic radius increases as you move this way. Metallic character increases this way, and non-metallic character increases that way. Have a go at the question, and I'll see you in class.